Hi, everyone. Thank you for joining. Thank you for having me here. My name is Dimitrios. I'm from Greece, and here are a few things about me. I'm engaged in computer security since 2002. I was member of one of the first reverse engineering groups back in Greece, and I started my career as a network security engineer for about 10 years. Then I moved into developing for almost 5 years, and the last 6 years, I focused mainly on mobile security. While before I joined Microsoft's threat intelligence team as a senior security researcher, I was leading another team which was conducting malware reviews for the Google Play Store. Besides that, I'm a father of 2, a boy and a girl. And in my free time, I try at least to write and play music. So before we start, just to get an idea of your background, do you have any Android developers here? Just hands up. Brilliant. OK. All right. So anyway. This is, I guess, justifies the short intro that we're going to have. So we're going to jump right into the outline of this briefing, which consists of the following topics. First of all, we're going to talk about some basic concepts regarding class loaders, parcelables, serializables. And then we're going to see some common security issues which may occur when we handle these objects in an insecure manner. After that, we're going to see what was the main motive behind this research, behind this idea. And then we'll see what we've tested until we finally concluded on the most convenient way in order to implement the exploitation technique for which I'm going to talk to you about. To see everything in practice, we're going to go through some showcases, some actual vulnerability showcases, and we will wrap up with conclusions and takeaways. All right, so ClassLoader is an essential part of the Java virtual machine, responsible for finding binary representations of classes, interfaces. And when these are found, the JVM constructs the corresponding class and interface and loads it into the application's memory. They are implementations of the abstract ClassLoader class, reflecting various loading policies. And they are organized according to an hierarchical model, establishing a parent-to-child relationship between them. On the top of this model, we have the bootstrap, or primordial class loader, which is responsible for loading the Java core libraries. And we also have user-defined ones, like extension or application class loaders, which are, they load secondary classes from extension or application directories, as their name implies. When it comes to loading a class, class loaders follow a delegation model, according to which the lower-level ones refer to their parents in case they themselves were not able to locate a specific class. This process will either end up on successfully loading a class or to a class not found exception in case none of the class loaders was able to locate the specific class. Moving towards Android operating system, performance considerations, as well as licensing and copyright issues, prompt Android to adopt the Dalvik VM. Whoops. Just a sec. Is it out? No. Ah, all right. The Dalvik VM was initially designed in order to address some of the JVM's limitations. Dalvik went through a lot of improvements until it was finally replaced by the Android runtime, Android 5. Despite all these shifts, the Android runtime maintains compatibility with the Dalvik bytecode, and actually the overall Android application development and deployment didn't change much through all these years. In terms of programming, Java remains a mainstay, besides Kotlin, of course. And when it comes to running bytecode, Dalvik uses Dalvik bytecode, which we can find in Dex files, and is not compatible with the corresponding Java bytecode. In fact, in order to create a Dex file, we need to use an additional tool in order to convert a class file to a Dex file that can be finally utilized by an APK. Some notable Android class loaders are the boot class loader, which is responsible for loading core libraries. And we also have the PathClassLoader, which is responsible for loading, which is the one actually assigned by default to every Android app during the initialization process. A few things about serialization, which in Java is the process of converting an object into a byte stream, which facilitates the transmission of this object across different JVMs. Either those are within the same machine or distributed on some kind of a network. For this process to be successful, the receiving end must be aware of the structure of the class of the received object, which means that this class file, the class file, must belong to the path of the received end's class loader. Now, in Android, moving objects between components is essential for inner and inter-process communication, so the adoption of an additional class, specially designed for this reason, was unavoidable. So Android, besides serializables, uses parcellables for classes that can be read from and written to a parcel. So these classes must implement the parcellable interface and must provide methods that can be used in order to read and write a parcel. If we want to create a parcel from the scratch, we can't use the constructor of the class of the parcel class due to the fact that this has remained intentionally private. But we can use the obtain method of the same class, which works as follows: dives into a pool of parcels in order to obtain one, and return it back to the calling app. When this parcel is no longer needed, it can be recycled, and so on. So deserialization can introduce vulnerabilities, assuming that the serialization source can be controlled by an attacker. MITRE assigned more than 690 CVEs for deserialization issues, and for prominent object-oriented languages like Java, .NET, Python, and so on. Android's own minimum reliance on Java vulnerable classes has raised the bar when it comes to crafting gadgets, as evidenced by the fact that very few of them exist in the Android ecosystem. Don't be fooled by that. Android is not immune to deserialization attacks, and here are some notable CVEs. When it comes to serializables, the first one that I'm going to talk about was discovered in 2014 by Jan Horn, who proved that during the deserialization process, the object to be deserialized was not inspected if it indeed actually belonged to a serializable class. So this allowed him to serialize objects of any class. And while many of you may think what bad can happen with that, the receiving end will try to cast this object to a non-fitting class and reject it or raise some kind of an exception. Well, during the garbage collection process, the finalized method of the binder proxy class dives into native code using a couple of pointers, which could be set by an attacker, could be controlled by an attacker. So Horn attacked the system server process with such an object, managed to get control of these pointers and get arbitrary code execution with system privileges. A year after, Pelez and Hay, in their paper, One Class to Rule Them All, they did something similar, highlighted a vulnerability which could once again allow an attacker to get arbitrary code execution with system privileges. This time, the researchers used a non-transient field of this class here, and by getting control of an 18 pointer, they managed once again to get arbitrary code execution with system privileges. Moving to parcellables, which are also not immune to this kind of attacks. Actually, there is a whole class of vulnerabilities which stems out of the mismatch between the read and write to parcel. The first most important one was discovered in 2017 by Mikhail Bednarski, who, by exploiting such an issue, managed to get what we call launch anywhere. Simply said, he was able to use the start activity with system privileges and an intent that he was able to control. And this allowed him to send this intent even to not exported activities. A few years after, the same researcher exploited a similar type of vulnerability, although in this case, he was able to get arbitrary code execution with system privileges. So it seems that the researcher community is aware of issues which may occur from insecure handling of these objects, and the developer community is aware of these kind of issues, and they are actually familiar with parcellables and serializables, since intents and bundles, which are some of the most commonly used classes in the Android operating system, are actually parcellable. There seems, though, to be a misconception when it comes to custom classes and objects which are created from these classes. And what I mean by custom classes, I'm referring to the ones which are created within an app. We can't find them in some kind of public repository or some kind of library. We can't import them in our project. So Due to the fact that Android apps are sandboxed, each one treated as a distinct Linux user, there seems, as I said, to be a misconception that one application cannot interfere with another application's class loader, which, as we're going to see, is wrong. So developers don't take the appropriate measures in order, as we're going to see, in order to protect this kind of objects. All right, now that we went through the basics, let's see actually what was the main idea behind this research. And I guess despite the fact that this slide explains itself, everything started while I was working on a project of mine, which I wanted to extend in order to monitor Android intents, which are exchanged between Android components, which subsequently led me to consider what might have happened in case a rogue APK was involved in this process. So after endless hours of programming, I managed to create a couple of scripts which allowed me to do such a thing. And here's how this extension, this feature, let's say, looks like. This is the Python version. For those who are interested, you can find some more info in this repo there. There's also a Java one. And this is actually a picture of an intent which is captured when it's exchanged between, as I said, Android components. Now, if we look a little bit closer, we're going to see that this intent contains a parcelable, which parcelable contains a field which is called entry URI, and it's actually URL. So the static review proved that the app, the receiving component, was adopting this URL blindly and sending there an HTTP request, which was authenticated. It included the user's tokens. So what if we were able to position ourselves in a way that we could create such parcels, send them to these components, and these parcels contain our own, let's say, data. So the first idea, in order to do such a thing, was a simple approach. It was to reconstruct the fully qualified name of the class, add fields which don't supposed to be null when they're received by the other end, and that's it, start creating objects. Take, for example, this case here, where we have a class which is parcelable. It has a simple field, a single field. So we can simply decompile the APK that we are targeting, copy the specific code within our project, add it to this package here, which is highlighted, and that's it, start to create objects. And this seems to work well for simple cases, though, because when we have more complex cases, things are getting a little bit strange. For example, imagine that we have this case here, where we have a class that links to another class, which links to another one, and so on. And to add to this, of course, the obfuscation, which is very common in Android apps. So imagine that we have to copy all these classes within our project in order to create a single object, which, as I said again, is impractical. The other idea was why we don't import the APK or the Dex file to our project, like a library, like an external library. This approach, although it is lesser known, it's pretty much straightforward. So the only thing that we have to do is just get the APK or Dex file, use a tool like Dex to jar in order to convert this APK or Dex file to a jar file, and import it to our project, like an external library. So once again, this works well in some cases, although it has two main disadvantages. The first one is obviously the size of the APK, due to the fact that it contains an additional one. So we have two APKs in one, I guess. And the other one, the most discouraging, I guess, is the following screen, is the screen here, which you get when you have a conflict between the libraries that you are importing and the libraries that are already there in your project. So you have to resolve these conflicts. You have to unpack the jar, I guess, remove all these conflicts manually, which, once again, is pretty much impractical. So it doesn't work. So what seems to work for us was dynamic code loading. And when it comes to Android operating system, dynamic code loading can be achieved with one of the many class loaders that Android has, including the in-memory DexClassLoader, the PathClassLoader, and the DexClassLoader, with the last two being among the most popular ones when it comes to Android operating system. Now, the DexClassLoader is a bit more flexible than the PathClassLoader. It takes as an argument a path to an APK, to a Dex file, and can be used in order to load classes from this file. The second one takes 2 arguments, a path to the installation directory of an app, and an optional parent class loader. So the problem here is that we don't know, we can't predict, actually, the installation directory of an app due to the fact that this installation directory contains randomly generated base64 strings. It's out of scope right now to describe how the strings are created, but we can keep in mind that we can't simply predict it. There are ways, of course, to get this info using some API calls, the package manager, for example. Although, why to do such a thing when we have a much easier way to obtain a class loader of another app? And here is the create package context of the context class, which works as follows. So it takes 2 arguments, the package name, for which we want to obtain a class loader, and a flag, or a set of flags, out of the ones which are depicted here. So when this method is used, it will finally call the create resources method, which will wrap up everything into a context object. And when I say everything, this includes the resources of this package, the class loader of this package, and we'll return it back to the calling app. Now, when it comes to the flags that I said before, out of particular interest, when it comes to this briefing at least, are the first 2, the context include code and context ignore security, which, when they are used in combination, they may allow us to execute code and create objects using the class loader of the package that we want. Few things to consider when we're using this specific method. So before Android 11, we could use the create package context directly, no extra steps. Is it out again? OK. Yeah, so we could use it without extra steps, although in Android 11 onwards, due to the package visibility restrictions that were important in this version, we need to take some extra steps when we want to use a specific method. And these extra steps regard the Android manifest. So if we know the package name for which we want to obtain the class loader, for example, we have to add the following entry here in the Android manifest. If we don't know, or simply we don't want to disclose this name, we can add a filter, an intent filter. So we can use the create package context for any app which matches the specific filter. Finally, when there's another way, using, for example, the query all packages permission, although if we want to publish such an app to Play Store, for example, we have to justify the usage of this permission due to the fact that it's regulated. And I can assure you that we can't say that we want to start exploiting apps. It's not valid justification. So yeah. So indeed, we can obtain the class loader of another app. And what we can do with that, we can, of course, use reflection. And for those who are not familiar with Java, reflection is a powerful Java feature which may allow us to create objects, inspect, modify them during the application's runtime. So basic components of reflection are the class, the field, the method, the constructor. In our case, we're going to use this method here, the load class, which takes as an argument the name of a class and returns a class object. So by using this class object, we can get a reference, among others, to the constructor of this class and start creating instances, as I said before. Here's an example of how this works. As I said, we get a reference to the specific class constructor, and then give the name of the class, define the fields that this class has, and then we can provide our own data in order to create an object, an instance. All right, so let me summarize what we have so far. So we said an app can access and use the class loader of another app as long as both of them are installed on the same device. They coexist. So these allow us to create objects of any class of another app, and by using, of course, our own arbitrary data. If the class is parcelable or serializable, then we can send it across components or across different apps. So what we can achieve with that? So The impact depends on the way that the receiving end will handle the data that this object that we have created, this evil twin that we have created, contains. And as I said before, developers don't take usually the appropriate measures in order to handle this kind of data. And this is why, in many cases, in most of the cases, we manage to get account hijacking, intent redirection in some cases, and even code execution in some of them. So what we are looking for when we're looking for this kind of issues, this kind of vulnerabilities, we're looking for specific API calls within exported components or components which communicate with exported components with the idea that these kind of objects may originate from an external entity. When we're dealing with intents, we're looking for get parcelable extra or get serializable extra, these kind of components. When we're dealing with bundles, we're looking for get parcelable or get serializable, and so on. Right, so what about the frequency? It is extremely frequent from the point that out of 300 apps that we reviewed, how they use this kind of objects, 156 of them were found to indeed obtain such an object from an external component, which means that these may originate, as I said before, from an untrusted entity. What about the impact? So in 31% of them were found to be vulnerable, and about 14% of them we managed to get account hijacking. As I said before, this was the most common impact in this case. 3% was found to, oops. All right. So 3% was found to be vulnerable to intent redirection, and 14% of them in other issues, including on execution, as I said before. Now, when it comes to where the classes of, what kinds of apps that we found this issue to be active, they're spread all over, including retail and e-commerce, travel and hospitality, media, and so on. All right, so now that we have everything in place, let's go through some actual vulnerability showcases in order to see everything in practice. And the first one that we're going to talk about regards an intent redirection. So for those who are not familiar with Android vulnerabilities, an intent redirection happens when an attacker is able to force another app to send an intent with data that he or she controls. It's one of the most, let's say, important vulnerabilities when it comes to Android apps. Even Play Store issues a warning for apps where this kind of vulnerability was identified and was not mitigated in a specific timeline. Now, let's go through the specific case. And what we see here is a code snippet which is taken from an exported component. So what this component is doing is checking the incoming intent for an extra which is called extra request. And if this extra request is present, this extra is present, it will check if it is of type request. And finally, we'll set it as an argument to the handle request method, which is highlighted below. Now, before we see what this handle request method is doing, let's take a look at the request class, which is actually abstracted and is extended by the iRequest. If we take a look closer, we're going to see that it has a field, an intent, which we can set, I guess, using the constructor of this class. So now, moving back to how this object is handled by the handle request that we saw before. So it will finally inspect it if it's of type iRequest, and it will be used as an argument to the start activity method. So we have a textbook case of an intent redirection in the specific case, and how we can exploit this specific code here. Use the create package context in order to obtain the class loader of this target package. Then load the iRequest class. Create a malicious intent. Let's call it intent 1, the first intent. create an iRequest object where we assign the first intent, the malicious one, create a second intent, which we add the next request extra, and we attach the specific object. And finally, use the start activity with the second request in order to get our intent redirection, as I said before. Now, the next showcase is about an account hijacking. And as I said before, account hijacking is one of the most common impact when it comes to these kind of attacks. So once again, this code snippet is taken from an exported component. And what happens here is that this component checks if the bundle is null, I mean the argument is null, which is going to be null in case the activity was just created. So then it will inspect the incoming intent if it contains a request which is called insider. This is supposed to be an article collection fragment instance. And let's see what this article collection fragment instance is, actually. So it is an insider class, implements parcelable. It's a parcelable class. It has two fields, a collection URL, and which we can set, of course, using the constructor of this class. So when we create such an object and we send to this app will adapt the collection URL, the URL that you saw before, and will send there an authenticated request, which includes the user's token. How we can exploit that? Once again, the steps are pretty much the same. Use the create package context to obtain a ClassLoader instance of this app, load the insider class, create an evil twin of this class using a malicious URL, a URL that we control, and create an intent, which has an extra, which is called the insider, and finally, send it to the target APK, so we got the user's token in our own server. The last case that I'm going to talk about, so there are many cases, actually, where in order to exploit a specific, let's say, vulnerability or a specific field, we have to provide some additional object, an additional object as an argument, or else our exploit will fail. So it was about a few months ago that I read the post about an issue in the Jetpack library, which may allow an attacker to, not necessarily an attacker, but someone, to initialize fragments, even if those fragments did not belong to exported activities or to exported components. This is actually a textbook showcase of what I just said. So we have such a fragment, which, if we take a look, it takes quite a few arguments, including a URL, and another one, which is called upscreen. Now, if you notice, this upscreen doesn't supposed to be null. It has the nullable set to false, and it is of type screen. So if we try to exploit the URL, assuming that this fragment will try to, this actually is a web view, so it will try to load this URL and send the user's tokens there. If we try to exploit that, we're going to get the following crash, which is expected due to the fact that the argument that I said before is required for this exploit to succeed. So the only thing that we have to do in our case, in this case at least, is to create a serializable of this class, of an instance of this class, the screens class, which is actually serializable. The payload is not here, it's the URL that I said before. And it's pretty much simple. We can even use the first method that I told you, just reconstruct the fully qualified name and so on. All right, so when this fragment that I said before receives the specific intent, it will take the URL, it will fetch the URL, and send there once again an authenticated request, which includes the user's tokens. So how we can exploit this type of vulnerability? Once again, the steps are pretty much the same. Create an instance, obtain, first of all, the ClassLoader of the other app. Load the screen class that we saw before, which is serializable in this case. Create a screen instance. Create an intent, which we assign the app screen and the URL extra. That's here. And final user start activity in order to send the intent to the vulnerable app. So we have, once again, an account hijacking in the specific case. All right. So this, I guess, summarizes what I just, yeah, so some issues here. All right, so the first key takeaway, you don't own your class loader. And what I mean by that is, of course, you own your code. You can change it, modify it, do pretty much whatever you want with it. But it's hard, if not impossible, to prevent someone from using it. And this, of course, includes borrowing your app's class loader and start to create instances of your classes. The next one is to avoid exposing parcelable or serializables object in exposed components, export components. I don't actually see a reason of doing such a thing, although I guess developers have pretty much valid reasons which I'm not aware, I guess. But if you have to do so if you have to do such a thing, make sure to take the appropriate measures in order to protect this kind of objects and be extra cautious with the data that they may contain, since, as I said before, they may originate from untrusted entities. Last thing, as you may have noticed, this type of vulnerability requires another app to be installed on the same device. And here comes the other misconception which I get, even, unfortunately, when I discuss this kind of issues with security engineers. And this is, what is the likelihood of someone downloading and installing an app, a malicious app, which can actually exploit the specific, let's say, vulnerability? So let me remind you that Play Store issues a warning for a vulnerability type which requires a third-party app to be installed on the same device, the intent redirection that we saw before. So I guess Play Store and Google don't take this kind of things lightly. From my side, I would say that it is a matter of how much you trust millions of apps which are, let's say, published in various marketplaces, and they're downloaded and installed by millions of users daily. So I wouldn't say that it's a matter of if such a thing may happen, but when such a thing may happen. So if you respect your users' privacy and safety, and you think you might have such an issue, make sure to mitigate these kind of issues as soon as possible. And with that, we concluded. And I will be, if you have any questions, I can take them. Thank you very much.